Sorry for the delay there, guys. Just a couple of problems getting Trev's laptop set up. Welcome again to the GTUG event. So good to see a good turnout here as usual. My name is Sean Murphy. I'm not a Googler, I work in UCD. There's three of us that run the GTUG, myself, Owen here in the front row, Owen Bailey, and Brian Farrell was able to make it tonight. Just a couple of things. The agenda, so you've had a bit of food, hopefully. First up, Trev Parsons, who's just walking in the room there. Good timing, Trev. Is going to talk about log entries, which is a system that they've been working on for the last, I guess, couple of years now, which looks at taking information from log files, and they've some problems scaling it up, which they've solved. After that, we have a bit of a break. Next up, Paul Phillips from Scrazzle is going to talk about some of the work that they've been doing, where they've taken a large corpus of data. I hope I've got this right, Paul, I'm not billing you incorrectly, and have done a lot of analysis, so analysis of all your sciences. Mark Ahern, unfortunately, was feeling a bit under the weather, so he cancelled. He should have had it more than 5 minutes. He cancelled this evening, so starting a bit late, he's not going to throw the agenda off any more than usual. I have a couple of things to say at the end, nothing very groundbreaking or important, but just a couple of points, next meeting and stuff, and then anyone who's up for a pint in the schoolhouse, as usual, we'll go there. Session's being recorded. If anyone has any problem with that, I think the only solution is leave. So we have a YouTube channel. We're a little bit behind getting everything set up on it. We have about 4 or 5 talks on it right now. There's 3 or 4 in the pipeline which are just about ready to go. So it will appear. There's a bit of a time lag on it, but it will get there eventually. Communications, #Dublin GTUG if you want to do some Twittery stuff. And dublingtug.org is where is our parsimonious web presence. And that's all I have to say. So I'll hand it over to Trev Parsons from Log Entries. So.
How's it going? I'll stand sideways slightly so I can see this. So my name is Trevor Parsons. I'm co-founder of Log Entries with Willem Holloop. We spun the company out of UCD back in 2010, and it was based on research that we had carried out in conjunction with UCD and IBM, where we had built a log management technology to handle lots of log data during system and performance test from IBM test teams that were building large-scale enterprise applications. So what we've done since is built a cloud-based version of the technology, and there were significant challenges with that in terms of being able to scale up to handle lots and lots of data from different customers, different organizations. The original challenge that we had to solve was how to consume and analyze log data from a single enterprise application. The new challenge that we have to meet is how to pull in log data, analyze it, and understand it when you're dealing with thousands and thousands of organizations. So that's been a significant challenge, and the title of the talk is Scaling to Process Trillions of Log Events Daily. So that's not something we do right now. At the moment, we can do billions of events, but it's somewhere we need to get to. Somebody's logs have gone berserk and the thing has fallen over. Okay, sorry about that. Right now we handle billions of log events daily, and our architecture can handle that quite well. But we need to get to a point where we're handling trillions of log events within about a year. So what I'm going to talk about today very quickly is what exactly log management is. A little bit about me and the company itself. Then I look at typical log volumes that are generated from companies of all sizes, and what is the spectrum of log data that's being produced out there today. And that goes from anywhere from millions of events from even very small companies per day up to about 1 trillion events from some of the largest players out there. And that's growing all the time. Then I look at some of the challenges from a technology viewpoint and how you actually handle analyzing and processing and storing that information and making it available in real time. And I look at that from an architecture and technology point of view. So we'll talk about our actual hardware, how the components are actually deployed, and what components we're actually using. So what is our back end made up of? What are the different technologies? What are the problems that we've had along the way in using some of the latest technologies that are out there, and how we've actually solved them? And we look at them in the context of the fallacies of distributed computing. So the fallacies of distributed computing were set out back in the 90s by Gosling and a guy called Peter Deutsch from Sun. And they were essentially the assumptions that people tend to make that aren't true and that cause distributed systems to break. Okay, so they're even more relevant today when you're dealing with cloud infrastructures. And what I wanted to do was look at some of the things that we've done over the last year or so, some of the assumptions that we made, how they broke our system, and how we resolved them. And they go from, minor bugs to actually some serious outages. And then finally, I'll talk about our next steps in terms of scaling to trillions of events. My beautiful assistant might fix that. So some of the next things we need to do in terms of scalability and where we're going to actually scale to the next level, essentially. Okay, so what is log management and why would you use a log management technology? So we often provide this logging story. Essentially, you have your coder. He's writing some nice code there. He has version 1. He decides to deploy it to the cloud or to App Engine or to whatever hosting provider he's using. He starts to get lots of traction. He's getting lots of users. Everybody's happy, generating lots of revenue. And suddenly, some evening, there's a serious outage. There is a critical error. And he wakes up next morning to find that the system is down. He's losing serious revenue, and his boss is not very happy. So it gets to a situation where that guy needs to go and delve into his logs, and anybody who's a techie will relate to this. So that's fair enough if you're dealing with a small development environment, but if you're dealing with a production system, it could easily be producing thousands, if not tens of thousands, or in some cases hundreds of thousands of log events per second. Okay, so you might be looking for something like this guy here in a couple of million events, so it's quite difficult. So that's where we come in. What we do is we grab your logs in real time, we analyze it, we pick out issues, we highlight them, we alert you on them, so that you can know immediately what exactly is happening in your system, where the problems are, and how to go about resolving them. So this is actually a real user account. You'll see over a week period, he's done 150 million log events. This is a website in the States. It's not particularly big, but it gets good traffic. He's got 3 exceptions in those 150 million events over the week. So looking for them with your traditional grep or your traditional Linux tools is going to be quite difficult. Okay, it's really a non-runner. So what he does with log entries is he logs in, he clicks on exceptions, and within a couple of seconds he gets those 3 exceptions. So you can very quickly see what those problems were, how do I go about fixing them. The typical end users we have are systems administrators, developers, test and development support, and also we get management and business analysts using the tool. And the main reason that we get both the techies and non-techies is because we've developed an interface that essentially allows anybody to use it. So anybody who can use Google search bar can essentially use log entries. Okay, so you can very quickly see different errors that exist in your application. You can use a search bar to search across it and pull out particular terms. And then the reasons that people use it, mainly to quickly understand what's happening across their system, and that can be from a system perspective, so you might be looking for errors or warnings, or it can also be from a business perspective. So you might be looking for the number of logins, number of registrations, that sort of stuff, and pulling out maybe problems with your payment process or something like that. And then finally, one of the nice things that we've done recently is we're building in automatic intelligence. So we're working with system vendors to identify what the error codes are for their particular components. So for example, we've done this recently on Heroku, where we've plugged in all of the Heroku error codes, so that anybody who is a Heroku user will automatically get out of the box that intelligence built into their system. So if they have a serious problem on Heroku, it'll be automatically highlighted for them. They'll also get automatic notifications if there's serious problems that could cause their application to fall over. So we're taking log management to the next step, essentially, and telling people what's going on in their logs without them having to actually log in and look at them. And I guess the spin we put on that, or the quote we put on that is, it stops your applications failing silently. So you know about a failure before your customers do and start complaining about it. Okay, and then the big opportunity that we see out there right now, and what we're going after, is in particular the cloud and platform as a service space. So if you look at the platform as a service providers that are out there today, they pretty much don't have any logging infrastructure. Okay, so it's hard to believe that people are running big, solid applications on platform as a service, because access to logs is very, very difficult. Even if you look at the most mature of the platform as a service products out there, like App Engine or Heroku, what they do is they give you a limited buffer to your log events. So you can usually tail events, but you can't look at what happened last night or what happened a week ago. Okay? And so if you have a particular error that occurred, that wasn't in the last couple of seconds, you're lost. You have no logs to use to actually diagnose that problem. Okay, so Google are addressing that. If you look at the roadmap for App Engine, it's one of the listed features that they're working on at the moment. It's building out that logging infrastructure to give you more access. The likes of Heroku are turning to companies like us to provide that as a third-class service. And so you'll see us plugging into more and more platforms over the next year. A little bit about me and my background. So I was previously a researcher in UCD. My background is mainly Java, but it's been about 3 or 4 years since I've been hands-on in that space, so don't ask me too many difficult questions when we get into the tech. I've been mainly involved in the business side of pushing out the business over the last couple of years. Our company, I mentioned some of this stuff, so I won't skip over it. We spun out of UCD. We're now in Dogpatch Labs. We launched our product halfway through last year, and we've been live since then, and we've been getting great traction for the last couple of months. So we're across the road in the Dogpatch. That's not actually the Dogpatch, it's just like this guy. That's the Dogpatch there. And it's probably one of the nicest office spaces, one of the coolest places in Dublin at the moment. One of the best things about it is there are about 15 companies at very similar stages. So all of the companies in there, they're startups, but they're all starting to gain traction. They're starting to get customers. So it's quite a busy place. It's quite happening. And from a startup perspective, it's great because you have great camaraderie there. You can turn around to somebody who's solving a similar problem to you, only the week before, and it's invaluable. It's not the sort of stuff you can sort of look up and read about when you can just turn around to somebody and ask them that sort of question. So I don't think we have time to go into some of the details. So in relation to scale and addressing the volumes of data that we're looking at, I pull up this slide on the data explosion. So The Economist magazine back in 2010 was talking about the data explosion problem. And when you see issues like this raising their head in mainstream media, you know they're becoming real problems. So they had some crazy stats about the amount of data that's being produced all over the world, and they estimate that there are 150 billion gigabytes of data created in 2005, and it's 8 times that amount. So I think to anybody that just means there's lots of data and it's growing, right? And so there's a big issue with actually handling that data and making sense out of it. In particular, when it's unstructured, it's very difficult to actually pull decent information out of that data. So one of the biggest contributors to the data explosion is actually log data. And log data is said to be the fastest growing data source today at large organizations. And large organizations are regularly producing terabytes of log data per month. Okay, so you might say, okay, well, what does that actually mean? So if you're producing a terabyte of log data per month, you're doing about 100,000 log events per second. Okay, so if you think back to the earlier slide when that guy was looking for that error or those 3 exceptions in his code, trying to find that in a 100,000 log events per second is impossible to do manually. So you need to start using tools to do that. So this is a slide that we stole from or borrowed from a blog by a guy called Anton Shovikin. He's one of the experts in the log management space, and he does a nice calculation that shows you how to get from number of log events per second to the actual log volumes. And this lines up with what we see in our own systems. And you might say, okay, well, how does that fit with my organization, and how much logs would we produce, or organizations of our size produce, and how relevant is log management for us? So what we have here is a spectrum of organizations and the typical log volumes we see being produced from these types of organizations. So it goes everywhere from your early stage startup that could be doing 50 events per second, which ultimately results in millions of events per day, up to your medium-sized organizations that might do about 1 billion events a day, up to the big boys who are doing 1 trillion plus events per day. And they're usually the telecom providers, the large cloud providers, and in fact, the numbers here are probably about a year old, so they're probably a little bit out of date, and the guys at the top are probably doing that a little bit more at the moment. But you can see the range that's there, and the problem for these guys to actually make sense of that information and pull anything interesting out of it. So we're operating really in this area here in terms of our customers. Okay, so we're focusing on the cloud space and platform as a service at the moment. And most of those guys are small to medium companies, or we're dealing with teams from larger companies rather than across the whole organization. So for us, we need to be able to handle thousands of guys that are producing billions of events, okay, which leads us to handling trillions of events daily. And as a log management service, scalability, uptime, and redundancy are paramount. You cannot lose any logs. Your system needs to be always up to accept logs from systems, and you need to be able to scale to handle variable loads. So these are the challenges that we've met along the way. Our architecture, we're based on EC2. So we use, obviously, EC2 for compute power. We back up our logs we store our logs on EBS. We back them up to S3. And the only other component that we're using from Amazon is CloudFront. So we use that for content delivery. In terms of the architecture itself, our front end is Django, and that handles any sort of user interaction or web interface and user data. Our whole back end is a Java-based back end. So it's mainly homegrown. We are using Cassandra. We were using Hadoop, but had issues around using Hadoop, mainly around our single point of failure. So while Hadoop is quite good on redundancy and it'll store your data across different nodes quite well, it's not great on high availability. So it has a master node, and if that goes down, you can't really access it and you can't write data to it. So where that becomes a problem, if you're using the cloud, in particular Amazon's SLA states that they will always have one of their data or one of their availability zones in a particular geography up at any time. Okay, so generally they'll have 3 availability zones per geographical location, and 2 of them can go down at any time. Okay, so if you're using Hadoop, which has a single point of failure, and it gets hit, you can no longer write data until that data center comes back up. Okay. So as a result of that, we've switched to our own distributed file system, and some of the advantages of that are it has lower latency. So another issue with Hadoop is that when you write data to it, it replicates the data straight away. Okay, so there's a delay there in the response time. So we built our own distributed file system that receives the data and then replicates it afterwards, and we get much higher throughput as a result of that. The rest of the backend is mainly is all Java and it's homegrown. So in terms of parsing the data, indexing it, and identifying particular events in the data, they're mainly algorithms that we developed through our research over the last 5 to 6 years. In terms of getting the data into the system, there's a lot of different ways in which you can do that. And essentially there's very few systems that we can get log data from. We have an agent that can be run both on Windows and Linux. It'll run out of the box on Linux. It's an open source Python agent. It'll send your data securely across the channel to your log entries account. We have an exe version for Windows. So that's available in our GitHub account if anybody wants to look inside it or contribute to it. We also accept syslog inputs. So if you're on a Linux box or you want to send your logs from your routers or your firewall, and most of those, all Linux boxes will support syslog, and most of the routers and firewall will do the same. We also have an API where you can actually log directly from your source code, and we've built a bunch of libraries that you can use that we've pre-configured with the API. So if you're a .NET developer, if you're a Python or Ruby developer, we already have pre-built libraries that you can just simply use out of the box and log directly through them to log entries. Okay, so what actually happens when we receive an event? When we receive an event, it comes to our API server. The API server is replicated across a couple of different data centers. The API server handles any real-time or near real-time processing. So it'll do indexing, parsing, and then it writes the logs locally. We then replicate the logs to a worker server. The worker server is, again, physically distributed, or the worker servers are physically distributed across different data centers. The data is written by the worker servers to the distributed file system. Metadata is stored in a Cassandra DB, represented by the DB here. And then we have our messaging server, which handles internal messaging. So it handles things like updates. So if you go into your account and apply some new alerts or new filtering to your logs, the messaging server will distribute that across the entire architecture. And then our sender servers will handle alerting. So they will actually do the alerting for us. And then finally, we have our web server, which is really our Django front end. That's pretty much separate from the entire architecture. Okay, so looking at how we built the system and the issues that we came up against over the last year or so, I wanted to do this in the context of the fallacies of distributed computing. So, as I said, these are becoming more and more relevant for anybody using the cloud. And there's a very good blog post from the guys at New Relic actually addressing these fallacies in the context of the cloud. And one of the points they make, which is very true, is that when you had your own network and when you had your own servers in-house, you had a little bit of a grace period before you had any catastrophic failures, and usually it was when you started to scale up. When you're using the cloud, you don't have a grace period. Amazon can fall over at any time, and it does every couple of months. If you're using any cloud services, they become unavailable from time to time, and if you do not design for failure, failure will happen. So an interesting point made by Netflix, who have their whole architecture across Amazon, was that they actually continuously try to bring down their own system. So they've designed for failure, but they constantly try and break their system, and they have what they call chaos monkeys, which are processes that try and crash their system consistently. And they find that without doing that, they're not going to find the holes in the system, and the system can actually crash in a worse way than when they actually try and crash it themselves. So the first fallacy of distributed computing states that the network is reliable. And in particular, if you're using the cloud and you rely on external services or APIs, the odds are not just high that your service is going to fail, it's a given. So at some point that external service will be unavailable. And whether that's Amazon or whether that's a payment process or a payment gateway, there's going to be points in time when that's not available. And you need to be able to deal with that and either respond to it or provide a service that isn't quite as high a quality, but that's good enough. And so the point made on the New Relic blog again was build an app that can function at reduced capacity when a given service is offline. Okay, so we looked at that, and we have to take into account, because we're using Amazon, what if two of their availability zones go down? What do we do about that? Okay, so when that happens to us, we can always accept log data. Now, there may be situations if that happens where you can't actually log in and see your logs, but you'll never lose data. So we'll be continuing to accept log data, we'll be continuing to write it, and we won't lose any data because it's replicated across the 3 availability zones. So we have built in reduced capacity functioning when there are major outages. So some of the other things that we've come up against, some of the less critical issues are the likes of when we've done some of our partner programs. So we've recently partnered with Heroku, and when somebody uses their application in Heroku, we take the Heroku header from Heroku and skin up our application so that it looks to the user as if they're still in the Heroku application or the Heroku UI. What we've noticed recently is that from time to time, that header is unavailable. Okay, so it looks when somebody comes from Heroku into our application that our application is broken because there's a network issue and we haven't been able to download the header. Okay, so how we've actually dealt with that is simply cache the header so that we can actually display it if it's not available. Okay, so there's just other little bugs that we found along the way when we've assumed that the network was reliable and the network is not reliable. Other sides that we've had to look at are in relation to our own agents. So if you're sending log data to log entries through our monitoring agent, the network's going to break from time to time. Okay, so our agents have to be able to handle that. And so that goes for when you restart your server or when something breaks on our side. So we've built into our agents the ability to reconnect to our application when there's a problem. And that's a must. And one thing we have to be very careful about is as we roll out new versions of the agent, not to actually break that functionality, because if that's the case, we have to go and ask all our users to download and install a new agent, and that gets quite painful. One of the other issues and there's not as many issues on some of the other slides, don't worry. One of the other issues that we found here, which is quite interesting, was, and this was why we moved from using Hadoop, Amazon, one of our servers on Amazon, was just disconnecting from the network for about 5 minutes a day periodically for no apparent reason. And we guessed after a while that it was just some sort of hardware failure or hardware issue on that particular box. It was very difficult to see. We couldn't see any problems on our side. But it was actually the master node of Hadoop that was disconnecting from the network. So during those 5 minute periods, we couldn't write any data to our database. So again, that was just another example of where we assumed that the network was okay, and when it broke, we had some serious issues. In relation to latency, latency is not zero, in particular when you're moving lots and lots of data around. So one of the things we've had to do, obviously, is use CloudFront, in particular where you've got customers from all over the world. So it's quite effective, actually, in serving up pages quite quickly to different locations. So that's worked quite well for us. One of the other issues we noticed in relation to latency was that when we're actually accepting data, we need to be able to write it very, very quickly and tell the person sending that data that we've accepted it so that they can send more data. And that's one of the key factors in actually pushing huge volumes of data through a server, is acknowledging that data very, very quickly. So what we've started to do is write the data locally first rather than trying to send it to a backend, and then getting a background job to actually send that data to the backend at a later point in time. So that has allowed us to handle much higher volumes of data on the same server in terms of sending that data to us. So I'll be told to hurry up, so I might skip through some of these and just look at some of the more interesting ones. The topology doesn't change is something that is not very true for the cloud. So again, this is another one of the fallacies where people would have built systems and expected their topology to stay the same. The cloud is constantly changing. You're constantly bringing servers up and down. And if you want to be able to deploy new versions, if you want to be able to handle bugs, you have to be able to take parts of your system up and down and not take the whole system down at the same time. So replication, high availability must be built in, and you have to be able to bring up and down different parts of your system. An interesting use case of this was where, and anybody who's using Amazon will have seen this. Amazon sent out an email about 2 months ago to all their users telling them that they were going to restart all of their servers at a particular point in time, about 2 weeks away. So a lot of people got a shock and had to figure out very, very quickly how do they handle that and what do they do around it. So they did give you the option to go and reset the servers yourself, which was nice. But some companies, and there was a couple of highly published examples of this, some companies didn't get the email, and their servers were taken down for a couple of days. One in particular in the logging space that we'd know quite well, and it took them a couple of days to get their system back up. So they had assumed that the topology wouldn't change. It did, and it cost them dearly. So that's just something you need to be aware of, is that you can handle people turning on and off servers, and you can recover from it quite quickly. There's one administrator. There's not when you're using the cloud, and this is something that you have to learn to live with. So if Amazon does have an outage or does have a problem, you deal with a web page, and you deal with a status.awz.com or something along those lines. So you need to be able to, again, work with the Amazon SLAs so that you're not waiting on Amazon to bring up service so that you can bring your service back up. You need to be able to function on whatever their SLA actually tells you, and when they actually bring up their other data centers, you can go back to full capacity again. Okay, so in terms of our next steps and challenges going forward, as I said, our current deployment is handling billions of events per day at the moment, and there's 3 ways in which we can improve that. So we can look at vertical scaling, which essentially means we get bigger boxes. Okay, so that buys you a bit of time. You can get more powerful CPUs. You can push more data through each of the different servers that you have, but ultimately you're going to hit a limit at some point. And at that point, you need to spread the load horizontally. So right now, there are current options in terms of increasing load when that comes. So, for example, if we expect a big surge from a partnership that we do, we buy a couple of bigger servers, we deploy a few more horizontally, and that holds for a point in time. However, going forward to handle the volumes of events that we're talking about, we need to constantly optimize how we handle that data. And what we're looking at right now is to more aggressively split the handling of real-time data, soft real-time processing, and background jobs. And so when we looked at the architecture previously, at the moment in the API servers, we are handling real-time data, or real-time processing, which is essentially receiving the data. We're also handling some soft real-time processing, which is doing things like indexing, tagging the events, configuring alerts, which need to be done within a couple of milliseconds. But what we're looking at doing now is splitting those and moving that soft real-time functionality to our back-end servers. That then allows us to split that load across distributed servers on the back end and push more data through our front end. Okay, so it allows us to receive much higher volumes of data on the given architecture, and ultimately to get to processing trillions of events and to keep your costs relatively frugal. That's what we're going to need to do. Okay, that's it. Any questions? That easy. It's actually not too bad. Yeah, so the question was, is there any issues spinning out of a university with intellectual property? And the university is actually quite good. They're getting better. And in our case, there wasn't any major issues. We were lucky in that we didn't really take any IP out of the university. We rebuilt a new service, and all we really took out of the university was what we'd learned. We didn't take out any patents. We didn't take out any actual code. If you're looking to do that, what they'll do is they'll do a license agreement. So you can, if for example you develop something during your PhD and there was a patent taken out on that, you can then license that from the university and you get some royalties back. There are problems with that in terms of if you're looking at your business model down the road and you're looking at investors, there's pros and cons. Some investors like to see patents. Some guys would be scared in relation to the university owning it. So my advice would be try not to take anything out of the university. But then you might ask the question, well, why would you be spinning out at all? So I could talk to you in length about it if you want later on, maybe. What do you mean exactly? You might have to explain that a little bit to me. Yeah. Yeah. The way the database works is we create a new file for each log file. And so you can think about it as maybe a table or a column in the database. And each user has a key, and only they can access that through the unique key. I think it's a 128-bit key. So there's no issues with people potentially crossing data over, if that's what you were wondering in relation to that. Yeah, to be honest, I'm not sure the answer. You'd have to talk to Willem, who's our database expert in that one. Yeah, did you say something about Linux data? I just didn't catch the full question. Linux. Yeah, so the question is just so I have it right, is that can you also, apart from putting out system information, errors, warnings, etc., you can also put out analytical information for business analytics? Yeah, so you can do both, and it really depends on what you log. So if you log, information about your business, when people log in, when people sign up, if payments are made, if there's payment failures, for example, which maybe crosses the line between system issues and business analytics, we find a lot of people using it for that purpose, in particular in early stage companies. So they're often interested in the business side, how many registrations are going on, but interested in it from a systems operations perspective. So are there problems with the payment process? Is it affecting the business? What is that problem and how do I fix it? And we have, in particular, CTOs of small companies using it for that perspective, so they get a full view of what happened over the last day, the last week, from a business perspective, but also they can see if there are underlying errors that were affecting the business. Yeah, absolutely. So, yeah, so the question was, does that also apply for user data? So if, for example, you have a user logging in or a user making a payment and you had a problem, at a particular point in time, can you use log entries to resolve that? And so we have people using it for that today. So we have support teams, and in particular we have a newspaper, an Irish newspaper using it where they have sign-ups and they don't really have a technical team. To have one support person who's their technical guy, and he's not really technical, and he uses it for that purpose exactly. So when they have somebody saying my subscription isn't working properly or my password isn't working, they go in, they check the logs and say, actually, somebody else logged in with that password 2 hours ago. You're sharing your password or whatnot. But yeah, for that exact purpose.
In your load testing, how high? In your load testing, how high was their transactions percentage?
I'm trying to think of the actual numbers of events per second. I'll get back to you on that one. I know we were doing over 1 billion events a day. Right now we're doing, with live data, we're doing about 200 million events per day. And our load testing pushes up to over 1 billion events per day. And I just can't think of exactly what that relates to in terms of events per second, but I can find out and tell you. Yeah, yeah. The question was if we're looking at new ways of visualizing the data, in particular for certain use cases. So, for example, if you're looking at network routers, for example, we're always looking at new visualization techniques. What we're looking at the moment is actually building out reporting. So, ways in taking the data and building out new reports. Not so much looking at particular visualizations for certain niches, but it's something we'd probably look at down the road. But then again, if we saw something really cool that jumped out at us, we'd be interested in looking at it, you know. Yeah, so actually, one other thing we're doing that allows people to actually use different visualization techniques is building out an API so that you can pull the data out of log entries yourself. Right now, you can do it through the agent. So our agent gives you command line access so that you can push up logs from your command line, and you can export them down and filter them out through the command line, and you can use that to access logs and to pull out particular types of events and filter them out. But what we'd like to do is expose some of the analysis that we do through our API, so then you can go and visualize it in different ways depending on what your requirements are. So that's something that is on our roadmap.
Hadoop, you had some quite negative experiences with Hadoop, clearly. Was the Hadoop that you were using Amazon's Hadoop, or
Was our own Hadoop? Well, not our own Hadoop, but
you didn't use Amazon last time?
no. I don't think so. As far as I understand, the main problem we had with Hadoop was the master-slave node architecture and how people have resolved that. So, for example, Facebook had built their messaging, their new messaging, well, about 2 years ago on Hadoop. And how they solved it was they had 2 identical deployments. So if one went down, they had another identical deployment. Now, that gets very costly, or at least more costly, and it was something we didn't want to do. So we had to find another way. And so what we found was to have our own distributed file system so that if any of the nodes go down, we can always write to one of them. Now, that's not to say we won't use Hadoop in the future. So we could use Hadoop for some of the offline jobs that we're looking at doing over the next while. And similarly, you know, we're using our own indexing algorithm. We're not using what most people in the space are using, which is Solr. And again, we found some issues with that, using it from our perspective. And we see some of our competitors actually have run into those issues since, so it looks like it was a good decision. But we would look at using some of those technologies in the future for some of the things we have planned.
One of the key points you mentioned was the speed of your file system needs to be very quick. At what point do you actually write data to this? Like your API servers, you just store things in memory?
No, so we write them to local storage when we receive them on the API server, pretty much immediately. And then we take them in the background from that and write them to, or send them to our worker servers, which is our distributed file system. They then spread them across different data centers so that we have redundancy built in. It was with Hadoop actually. So we had delays with Hadoop, but since we've written a more simple distributed file system, which is I think based on NFS file systems, it seems to be a lot quicker. So we can write data much quicker. There was one other question maybe. Issues that we saw was that when it fails badly, and often you have to re-index the data. and that can be very, very slow. So that actually happened to a company in the States in our space where they had an outage as a result of Amazon, and it took them 3 days to rebuild their data index. So it was pretty poor.
So surprise, surprise, we're running a little bit late. We'll take a, I guess, 2 or 3 minute break. It's 1949, so let's say we'll be back at 5 to 8, and we'll get going then. All right, guys, everybody's got their seats there. So next up is Paul Phillips, the CTO of Scrazzle, who's going to talk about analyzing science.
Hey, how's it going? So I'm Paul Phillips. I'm going to talk about Scrazzle. Sean actually came up with the title for this talk, so it wasn't me. Analyzes the Scrazzles or whatever that was. That wasn't me. Yeah. So just a little bit about our team, where we've come from, and then I'm going to go through the products that we've built. And then give a little bit of background on the technology behind those products. So we've got 4 engineers, and Dave, our CEO, who's smiling smugly back there in the background. Our engineers, 3 of us came from Hostworld, and Mauro came from Populous. So Trevor's already talked about Dogpatch a little bit. He lied though, the best part about Dogpatch is definitely the pool table. And is also the worst part about Dogpatch. So the idea behind Scrazzle, Dave was doing his PhD, and it was in the area of life science. And during his PhD, he was reading a lot of these research articles, and it was quite difficult to find information about products within those articles. So we'd be reading the articles, coming across a product that may be interested in, but finding it difficult to find information about that. So it started with that kind of core concept, quite difficult to find validation about products. So should I use this product or not? How many other people have used this product before? How many articles has this product appeared in? And it was quite time consuming to find this information out himself. So we wanted to open up the information extracted out of the articles and provide a way for scientists to basically be able to decide whether a product was useful or not. And at the same time, we wanted to help manufacturers as well, because that's what we were going to sell. We were going to sell the information about their products. So they want to see how their products are trending over time in research, how their brand is trending and that kind of thing. So we have 4 products at the moment. The first one is highlighting. So as a scientist is reading a research article online, we basically analyze the content. We highlight entities that we recognize within the content. The scientist can click on that, so it could be a product. They get a little pop-up with supplementary information about that product, a description, and some other information like rating, how many other articles have included this product. And then they can go through to Scrazzle.com itself. So Scrazzle then has a collection of all these products. You can see the information that we have about it, what articles it's been mentioned in, how many people use it, see reviews, questions and answers about that, about those products. So this is the analytics. So this is what we sell. It's kind of hard to see there, but basically we analyze all of the kind of the content, full text content of research articles. We pull out information about the products that we find, the brands that they're associated with, and then we feed it into our analytics system and we sell that to manufacturers so they can see how their products are performing over time, what their share is in comparison to other manufacturers that they choose to look at, what journals their products are appearing in the most, or what journals their brands are appearing in the most. And And then we have feeds, so we try to distribute that content across the web then, so we can give the manufacturers widgets. So for example, a citation widget, whereby they put the JavaScript widget on their page, and we deliver the citations in which that product has appeared. So I'm just going to quickly do a demo, hopefully. Okay, so this is a very basic demo that I put together earlier. So this is a research article, and just a very basic example. So we highlight the product within the research article. You can click on it. You get the description, a little bit about information about it, the rating, how many people have used it, and how many articles it has appeared, and then you can click through to Scrazzle. And you can see then the rest of the information, and you can add content yourself, reviews, questions and answers and that kind of thing. From an analytics point of view, what we sell to the manufacturers, this is our analytics. So we've 3 different sections, or 3 different things that we analyze basically. Brands, phrases and products. So a company will sign up with us, they'll say, right, we're Merck. We'll analyze the content that we have, pick out Merck within the documents, and then track that over time. And we do the same thing for products and phrases. Now, brands and phrases, they're not actually too bad. They're kind of easy. It's just a basic string search. Let's see. But products are a little bit trickier. So this is a kind of a simplified overview of our architecture. We have web tier, which is just obviously delivering the web. We have a kind of a tools or analysis tier, which basically that's where we do all our work. So this revolves around centralized job queue. And within the job queue are individual tasks, and then various different analysis servers can pick off work off the queue and do that. From a database point of view, we use Solar, which is awesome, Trev. We also use Mongo and MySQL. So the Scrazzle.com, the web servers, I'm going to go through the web, how we analyze, and just talk a bit about those. So this is the tech stack that we're kind of using on the web tier. So Varnish, caching, Nginx web server. We do everything, well, nearly everything in PHP and Zen framework. We do a little bit of Python as well. That's usually for NLP stuff. And MySQL is the backend for the website. So just a couple of things. I'm going to kind of pick out a few points from each kind of section that we found interesting or a little bit challenging. Deployment. There's a good few different options in terms of how do you deploy to various different web servers. So if you have 10 web servers, how do you deploy quickly? We chose to do Git-based deployments. So we've got basically have a minutely cron, pulls from master, and that's across all the web servers. This is really cool, but also really dangerous. But it works well for us. It's nice and simple and quick deployments. So basically, we work off a develop branch. Once we're creating a certain feature, we'll create a branch for that feature, merge it into develop, and then one of us will merge into master, do some testing, and then just push master to the remote, and then it's on the web servers. Configuration. This is kind of an annoying one. Configuration is kind of easy when you're at 1 or 2 web servers, but once you go above 10, 15 servers, and there are different types of servers, so they're web servers, analysis servers, database servers, it gets a bit frustrating. So an example is we do some testing on Solar, So we want we want content indexed into different solar setups, so different schemas and that kind of thing. And because all our configuration is working off Git repo, so it's just one file, it gets a bit messy after a while because you're managing lots of different configurations. So we're looking at Doozer and Zookeeper, but not sure if we want to go there yet. So scaling from the point of the web tier, it's kind of comes back to what Trev was talking about earlier on. The one thing we do is assume that every machine can disappear at any time. You have to do that on an individual node level with AWS. So what you got to do is ignore the file system. Say, for example, user profile images that are being uploaded, you don't upload them to the local machine, they go onto S3. Another example is sessions. We have our sessions on the local box, but we will move them off. If say, for example, one of the machines falls over and you have your sessions on that machine, obviously someone who's logged out or logged in will get logged out, that kind of thing. So it's a bit, it's not great, but that's the kind of stuff that you need to do. You need to assume that the machines will fall over, and then you need to ignore things like file systems, that kind of stuff. So from a highlighting point of view, how do we actually, how do we do it? There's two main parts, indexing and analyzing. So from an indexing point of view, we use Solar. It's actually pretty easy to use, but it's quite difficult to find out information about how best to use it. So we did a lot of kind of research looking into how best to set it up with large document sizes and a large number of documents. And the information isn't really out there. It's a lot of, well, it depends on how you're using it. So we have about 25 million documents. About 4 or 5 million of those are full text articles that we've been given from Elsevier. And they're probably the most difficult to index because the other 20 are abstracts, so they're quite small. So small documents, easier to index, better performance, we found, depending on the servers. So we have that spread across 3 servers at the moment. So for us, we have to index the content by sentence. So when we're analyzing, we can't identify a product in one sentence and have the brand at the start of the next sentence. So we're doing proximity searches, and they have to be close together and they have to be in the same sentence. So we're using a multi-value field to do that. So one document represents a research article, and then one of the fields in that has all the sentences broken up. It's actually a little bit trickier than I expected, just breaking it up into different sentences. Things like Dr., Mrs., when they're in the sentence, you've got full stops where you don't expect them. So we use NLTK to split them up across different sentences, but even still, that doesn't get it 100% right. So, for example, in scientific research articles, what you have is even catalog IDs. They'll say, oh, we use product X in brackets cat.12. And it always breaks it on, it'll say that's different sentences when it isn't. So what's required there is you have to train it, you have to give it thousands of examples, shoot it into the engine, and then eventually it'll learn that they're actually the same sentence. So performance factors that are things that affected the performance of Solar. When indexing large number of documents, large document sizes, we had to distribute the workload. That was pretty important. Commit frequency was another one. So at the start, we were committing quite often. We thought that was a good idea. That's not a good idea. So right now, we commit after, I think it's every 10,000 documents. Data size, so the amount of data that's gone into it is also a big one, but that's more in terms of query performance. Solar is pretty attached to memory, so a lot of memory is always a good idea. It has a lot of aggressive caching. So when we started indexing the content into Solar, it was taking us about 3 days. And I think this is what Trev was talking about earlier on. One of the big kind of problems with it is it takes a long time. So what we had to do was we had to split it across multiple servers, and we had multiple workers taking from that job queue. So taking a task off the queue, taking a document, going right, shoot it into one of these servers. So doing everything in parallel, distributing the workload. So then we got it down to about 9 hours. That's on 2 machines, so it can definitely be done quicker again, and they're only about medium size. So you're talking about $500,000 an hour. The obvious knock-on effect of doing distributed indexing is that you now have distributed search, so you have to take that into account. Luckily enough, Solr takes this into account if you set it up properly, so you can basically say, you go to one of the servers and you go, this is my query, and these are all the other servers. Now merge the results for me. So from an analysis point of view, it's the same as what I was talking about earlier on. So it's a Gearman type approach. You basically have one queue server. We bring up multiple analysis servers, and each of those has workers. So you can say bring up 10 analysis servers, and we'll have 10 workers on each, and they're all just pulling from this one job queue. So each task on the queue could just have the product name and the brand name that it's supposed to go off and do work for, which basically means you're distributing the work and getting things done faster. So how do we do the, or what's the process for actually highlighting the products within the sentences? We already have got the sentences indexed across, or sorry, the content indexed and split into different sentences. So now we can do a Solr proximity search. So that will basically return us the documents in which we've got sentences that have these things close by. And then we have some filters, and they basically take the results and look at it in more detail and go, okay, is this product actually associated with this brand? Is it the right product? Things like substrings. So if you have blue bottle and it's just bottle as the product, then you need to be aware of that as well. And then we store the results in Mongo. So the filters themselves, so it's basically a chain filter system. So a filter gets a sentence, it then does its thing, and if it's a rejection, then it throws it away. It throws it onto the next filter. And each filter is responsible for different types of identification. So one filter might be just checking the exact product name followed by the correct brand name, and other filters will take into account NLP stuff. So if the product is a multi-word product and it's split up, so we have some words in there that we don't recognize, we can shoot it into NLTK, and we can use a part of speech tagger. And basically what that will do is say, right, well, these are nouns within the sentence, these are verbs, and that really helps you make a decision. So if it's a noun that's in between the product words, then you may have a problem. So how do we improve then? We create more filters. Our NLP at the moment, it's in 2 parts. One is basically where you ask it for a part of speech, and the other is going to it and say, right, here's a sentence, identify the product for me. That part is a lot trickier. We're working with Derry Research Group in Galway to get that accuracy a lot higher. And then the other thing we're looking at is having a multi-threaded PHP setup. So at the moment we can basically launch 10 analysis servers, go onto each of them and launch multiple workers. But it would be far more efficient if we just say, right, 10 analysis servers, and here's the thread that you need to run, and it goes off and manages the whole process. So from an analytics point of view, this is more focused on the kind of the database side of analytics. We needed something that was easy to set up, and that was important. Obviously, fast writes and fast reads. Writes was probably more important because we were doing analysis where we were inserting a large amount of information. And then once we go live, we'll still be inserting quite a large amount of information. Reading, not so much. There's far fewer manufacturers out there that will be actually using it than us inserting into it. So the data that we've stored in Mongo is our articles collection, so the meta information about the articles, the hits, so the results of our analysis, events, so if you click on a product within a research article, we'll capture that, and then aggregation just for reporting. So we went with Mongo. We went with it because it was easy to set up. There was common kind of theme going through the industry about its use in terms of analytics, and it had a PHP driver, which was handy. But as soon as you begin to scale up Mongo, it becomes a little bit trickier. So when we first started using it, we only had a few hundred megs of data or whatever, but now we're about 30 or 40 gigs. And the main thing with Mongo is that you really need to keep that in memory. So you've got your index and you've got your data. And if you can keep all of that in memory, then awesome. But if you can't, you're going to start running into performance issues, and you're going to have to start sharding. So it gets more complicated fairly quickly. You're going to be dealing with primary and secondary nodes, arbiters, which is basically going to be voting if a primary goes down, who's it going to promote, and then configs, which is basically saying, right, well, which shard do I actually send the writes to? So it was easy to set up, but it gets complicated fairly quickly. Performance, so 20,000 writes per second is fine for us. Key factors, again, the index and the data in memory if possible. SSDs are suggested quite a bit, but that's a bit crazy. So that's pretty much it. That was a quick overview. We have the web tier, our tools analysis servers running off centralized job queues. We have our sharded Solr servers, same for Mongo, and then MySQL as the content backend. That's it. Any questions? We're going straight. So it was basically, are we using the driver directly into Mongo, or are we using some sort of mapper? We haven't had any issues with it. I did think about it, but I guess it wasn't a huge issue because the way it's set up, it's fairly easy. We would just want to go, right, well, what's the count for this, or get this particular source event. We don't have a huge number of collections in there. It's just that there's an awful lot of data within the collections. So it's not massively complicated in terms of retrieval or writing. Yep. Sorry? So, did we do it by hand? Is that what you're asking? So, did we do any of it by hand is, I guess, the question you're asking. So, the indexing, or the analysis, I think. No, so none of it is done by hand. So what we do is we basically looked at, verification is done by hand, right? So verification is done manually. So what happens is we built a filter that we think will pick out a product successfully, and I associate that with a brand in that sentence. So once we do that, we give it a shot, we run the analysis and see the results that come back. Then we'll pick out, like, say, a statistically significant sample of the results, and we manually verify those and go, all right, okay, that's correct. And then you have, say, 95% certainty of that particular filter being accurate. So we assign confidence scores to each of the filters. So there's no actual kind of manual analysis being done, but what we do is we verify the results and then associate a confidence rating with those. Not for every product, no. It's just for patterns that we recognize. So we'll say, right, well, product X was purchased from brand Y. Fairly common one, really easy to do. Just throw that into filter, so it's not any particular product. But then there's far more complicated ones where you have the words of the product split up across different parts of the sentence, and attributes of the product as well. So it's not just the product name. Things like antibodies will be monoclonal, polyclonal, this kind of thing. So you have to take that into account as well. If it was mentioned anywhere in the sentence, and that kind of fires off a warning saying, right, well, we have to look at this sentence in a little bit more detail, and then that'll shoot it into the kind of antibody filter. So it's more of categorization of patterns and problems as opposed to looking at individual products. Yep. In like all of it. Yeah, so looked at Cassandra, read a little bit about it. I kind of wanted to use it because I can't remember what it's called now, but I think it was Twitter that basically had their analytics system built on Cassandra, and they were going to open source that, and it was basically this. So you've got massive amounts of data, and now you have an analytics system sitting on top of it that's really performant. So I wanted to do that. A couple of problems. One was Cassandra was apparently a bitch to set up and manage, and the other one was they didn't open source it at the time, so it wasn't available. Yep. So we make deals with the publishers. So we've made a deal with Elsevier. They've given us all their content. So we're allowed to analyze, index all of their full text articles. So we've been making deals with each of the publishers. Sorry? No. So I think there's a number of different publishers around the world, and they all have their content in different formats. So we're not aware of those formats yet. So to build an interface where they can upload that, or there's a lot of data as well. It's not really pushing one article to us. It's basically pushing millions of articles to us. So yeah, I probably won't be doing that. Yeah, looked at it. So Elasticsearch instead of Solar. Yeah. So looked at Elasticsearch, but when we were setting this up, it was pretty young. So there wasn't a lot of features in it yet. But we're still looking at it. I mean, the good thing about this setup is that Solar itself is basically hot swappable out of the system. All you need is the index by sentence and a proximity search. So it's fairly separated out. If we do want to go with Elasticsearch in the future, it's faster indexing or faster queries, then it shouldn't be an issue. Yep. How many languages in terms of PHP, that kind of thing? Or actual languages? So it depends. So if the product is in Spanish and the article is in Spanish, then we support that right now. If that's not the case, then we don't. So basically, we take a product and we try and analyze that across the content. So we don't do any translations or anything like that across the content. We just take whatever format it is in now, whatever language it's in now, and we just analyze that.
How far down the natural language moment you're pulling out product names, new terms, I guess, and the whole macro bank process, there's a whole lot of sophistication in it. You bring that forward for different purposes. Do you know how much marketing you're going to have there?
So, question is how much effort are we going to put into the NLP stuff and how far we're going to go with it? Ideally, not a lot. I think it's a pretty complicated area that people haven't solved yet. So, really, I'm looking at NLP from a point of view of just connecting that gap where we haven't managed yet ourselves. So, just using part-of-speech tagger, that kind of thing, using what we're working with Derry. Even if it's only 50% accurate, we can use it to verify information. So not using it as a primary source, or using it as a primary source where we later verify. We basically, I think it's a huge amount of effort to get the NLP side of things right up there to be 100% accurate, 100% recall, that kind of thing. Yeah, no. So I think you can solve it in easier ways in combination with some of the NLP stuff.
There you go. Can I just use your laptop? So, just a couple of announcements just before we wrap. A couple of announcements before we wrap. No, that's not where I want to go. I hope this should work. Damn. I didn't, sorry? Let's sign out, okay. The whole point of putting it on Twitter was to put the wrong link on it. No. No, this is. So, do you have the clicker there, Paul? Okay, so I'm not going to talk about this because we don't really have much time. We did an Android Dev Camp a couple of weekends ago. We didn't have huge outputs of it. I think probably the key output of it is Owen's Hit the Road app, which I'm sure he'd be interested in people playing with or testing. Is it live yet or yeah? So a project that I was working with Anthony, I don't know if Anthony's still here, was an accelerometer project which I can talk to you about in the pub if anybody's interested. It was quite fun. So some kind of arbitrary notices I kind of normally put up here. Google I/O tickets still haven't been released for that. Startup Weekend, Ben, I think, has left the building. Ben Curdy was one of the guys who's organised the Startup Weekend. It's on March 2nd to 4th, which is this weekend. It's on here, I think, in this building. All the tickets are gone, except you can get a ticket, I think, for the show and tell on Sunday evening, if anybody's interested and going along to that. Probably check out the Twitter hashtag SWDub to find out more details on it. We're having an AppScript hackathon on March 13th at 6:30 p.m. I think probably in here, although, is Jean here? Is it in here, Jean, do you know? Okay, well, you'll find details on the mailing list. A couple